This screencast illustrates various concept and sampling-based planning. Let's consider a state space that consists of a couple of obstacles, a starting position, and a goal. The problem is now to find the shortest path between the starting position and the goal. This is a simple 2D example, but it could be any dimension. For instance, in a state space which has 6 degrees of freedom, such as x, y, and z position and pitch, yaw, and roll, or the multidimensional degrees of freedom of a high-dimensional arm, where each axis in the state space corresponds to a joint angle, for example. Usually the state space is bounded. These are either obstacles that cannot be penetrated or simply given by the kinematics of the robot platform. Let's say we have a bounded state space like this, and the robot is not able to actually leave that state space. Common to all sampling-based planning techniques is that points on the possible trajectory of the robot are sampled randomly. For example, we can start from the goal, pick a random point, connect it to the start, pick another random point, connect it to the start, pick another random point, and connect it to the closest point in the tree, pick a point, connect it to the closest point in the tree, pick a point, and so on, and eventually find a path to the goal. How do we know that we actually reached the goal? In practice, what you have to do, you have to define a goal region for which you are happy when you enter it. So let's say we define the goal region as a so-called D ball. In this case, D is 2, so it's a two-dimensional ball or a circle, and we stop search once we enter this region. So let's say we take another point like this, and finally sample a point in the goal region and find a path. There are many different ways of how to select the next point to test, and those depend on the actual algorithm and the problem that you want to solve. One way of doing it, and this is what we just illustrated, is just taking randomly sampled points that are uniformly distributed. One can show that this approach actually biases the search towards the largest Voronoi region when considering a Voronoi partitioning of the existing points. For example, the red lines show a Voronoi partitioning that has been done between all points that are currently in the graph. One can now easily see that it's more likely that a future point is selected in a larger Voronoi region than in a smaller one. For example, it's very unlikely that we select a point in here, but it's more likely that we find a point in here, thereby growing the tree in a direction that has not been explored yet. There are two methods that are commonly employed to speed up the search. Let's consider an example where, again, we have a goal somewhere here and a start somewhere there and a couple of obstacles in between. Let's assume this state space of the robot would be the entire screen. Now if we start to take random points close to the start and start growing the tree from those, we will get something like this. Obviously, it would be much helpful if we would start from the goal as well in the same fashion. So now every time we add something to the start or to the goal, we can look whether we can connect the two trees somehow. So if you do this, we will eventually come to a point where it is easy to connect the trees, such as this one where there is a line of sight connection, and we found a path. This approach is known as bidirectional search. Another way to speed up the search, that is finding a feasible path to the goal, is to actually pick a point close to the goal region every now and then. So let's say we put 5 points out that start from the start. 3, 4, 5, and then take a point at the goal. So now we can see whether we can connect the start to the goal, or the goal points to somewhere, a tree that started from the start, and we can see that we find a path like that. Of course, this doesn't work so well when we have obstacles that are requiring us to take a huge detour to the goal. Let's say we have a U obstacle like this, then it will take quite a while until we find a point that connects to the goal, therefore wasting valuable computation times whenever we try to get to the goal. Thus, this is a trade-off between speed and exploration time. It works well in some environments and in some it doesn't. This approach is known as goal biasing. How to deal with collisions? One way of doing it is taking sample random points and checking whether they are in a collision or not. So this point falls within an obstacle and therefore should not be other 2 than 3. This point doesn't. This point doesn't. This point again falls into an obstacle and we ignore it. This point doesn't, and so on. It turns out, however, that for some problems, doing something called lazy collision checking is actually preferential. In this case, what you would do is you would actually draw a path even though the point is in a collision and continue your search until you find a goal. That would look something like this. So we would start connecting things. Let's say we have some goal biasing here. So actually this is our path. Now what we would do is we would inspect the path only after it has been found. So we know this is actually a path, and now we actually spend only the time to check whether it's in collision. So what we can do is we can say, well, this path is in collision, or at least some segment of it is unusable. So we go and take out this segment and leave this point in this part of the segment, so these points intact. Now we continue our search and add additional points to the tree, and so we also use that segment that we have been not deleting and continue to draw our possible paths. Now let's do some goal bias again and we find another path. It turns out, when doing experiments, that doing a lazy collision checking can be up to 6 times faster than checking every single point for collision at the time when it is added. All variations of the algorithm that we've seen so far are known as single query algorithms. They are good if you have an unknown environment where there are dynamic obstacles and we want to find the shortest path every now and then. In environments where we know the configuration will not change, instead we can do a different approach. Here we can sample random points, check whether they are in collision or not, use only those that are not in collision, and connect them by feasible paths that the robot could drive. Let's say we have a car-like robot. This car could only make connections like this, for example. So you see, every time I add a possible path, it is actually following a kinematics constraint that a car might have. So now I can create a graph that is collision free and actually feasible when I would drive it with a car-like kinematics. So these are some of many possible ways of connecting these trees. Now if I want to find the shortest path between the start and the goal, I can actually just use standard graph shortest path algorithms such as Dijkstra's or A star to find my path. Let's look at this real quick, and by inspection I clearly see that if I want to go from the start to the goal, something like this path here would probably be my best bet. This screencast shows how a random path can be improved. Let's consider a start and a goal, and let's consider we have found a random path that connects start and goal, but is far from optimal. We cannot think about this path as the maximum path, and every path that we want to find is less than that. So we can now think about this path as a constraint for an ellipsoid, which allows us to construct an ellipsoid by stretching it out and rotating it around start and goal positions. So what we're going to get is an ellipsoid like that, which essentially tells us everything outside of this ellipsoid will be a longer path. We can now drastically constrain the search space in which we operate and say that we're only interested in additional points within this ellipsoid and basically improving the probability to find a shorter path. This goes on and we can create a smaller ellipsoid like this, further decreasing the search space.